Xfoil gives you the ability to manipulate airfoil geometry, as well as design and analyze airfoil shapes. For this reason, we're going to briefly review airfoil geometry in this video. This video is part of a series dedicated to the Xfoil software. It has lecture material and tutorials designed to help get you from absolute beginner to subject matter expert on the software. This series, of course, is brought to you by The Science of Flight, a new brand here on YouTube dedicated to aerospace engineering, education, and software. Let's get to it. On this slide, we'll talk about the basic airfoil geometry. I've got a nice illustration right there on the right side of the slide with a general airfoil shape. That general airfoil shape has a lot of the key parameters identified or overlaid on top of it, and they've been numbered. They're not numbered by importance, just by convenience of numbering, and we'll cover each of them individually. It's not really meant to be an in-depth coverage, but rather kind of a brief review or refresher in case it's been a while since you've taken your Aero 101 course. If you're looking for a more in-depth coverage, check out my other series I'm making on aerodynamics. I'll probably have several videos up in the near future kind of covering this topic more in depth. But let's just cover these briefly. The idea behind it is that Xfoil gives us the ability to manipulate many of these parameters, and so just thought it would be a nice review to make sure that we understand what we're doing when we're adjusting some parameters in Xfoil. All right, so number one, zero lift line. Now, I'll be honest, in all of my aerodynamics classes, we didn't really deal with the zero lift line per se. Rather, we dealt with the zero lift angle of attack. That's what we always stated or dealt with, or that was in all the equations we used. And the zero lift angle of attack is just the angle between the chord and the zero lift line. But that angle of attack is actually the angle at which the airfoil will not produce any lift. It's kind of like a neutral point. Once it starts tipping back, then it's going to start producing lift. So that's the zero lift line. If we had a symmetrical airfoil, that zero lift line would lie on top of the chord line. But since right here on the right we have a cambered airfoil, it actually does not lie on top of the chord, and it has that offset angle right there that offset angle of the zero lift angle of attack, zero lift alpha. All right, number two, leading edge. Now I've heard several definitions of the leading edge. I've heard the aerodynamic description of that's the leading edge is the part of the airfoil that the air touches first. I've heard of a structure's definition of it's the foremost part of the airfoil. I've heard kind of a geometric definition, I would say, where imagine if you took a circle that was bigger than the aircraft and put the aircraft inside of the circle, and if you slowly decreased the diameter of the circle until it was touching only 2 points on the airfoil, those 2 points would be the leading edge and trailing edge, and the diameter between the 2 points is actually going to be your chord. I kind of like that definition. It's got good visualization. However, a more technical definition would be that the leading edge and the trailing edge are the foremost or aftmost points that have the maximum curvature, or if you want to think of it, the minimum radius of curvature. So that's kind of maybe a more technical definition of the two. Now the leading edge, what's important about it is that it is actually used as the origin when dealing with airfoil coordinates. The x-axis of this coordinate system correlates to the chord of the airfoil, and the chord goes from 0 at the leading edge to 1 at the trailing edge. Now the y-axis of this coordinate system would be kind of the just the distance from the chord to the upper surface or the lower surface. So when you deal with kind of a file that has Xfoil, that has an airfoil shape, usually it's a list of coordinate pairs that has the x value of the location on the chord and the y value that is either the distance to the upper surface or the lower surface. So that leading edge is important because it's used as the origin for this coordinate system. All right, the nose circle, number 3. I haven't really used that in many of my classes. We just talked about kind of the radius of the leading edge, which I guess you can consider kind of like the nose circle. So that's kind of there for you. Sometimes you'll hear about it and use it, but I haven't dealt with that much myself. Number 4, thickness. Now this seems like it'd be an easy one, an easy definition. And it, for the most part, is. It's the distance from the upper surface to the lower surface. Now, however, the way you draw the line from the upper surface to the lower surface depends on what convention you're going to use, whether it's American convention or British convention, and we'll cover both of those on the next slide briefly. But just remember, the thickness is the distance from the upper surface to the lower surface. And the maximum thickness is one of the important parameters that you'll hear a lot. You'll also hear the thickness to chord ratio, which is just the maximum thickness normalized by the chord distance. The C right there on the diagram, the chord being just the distance from the leading edge to the trailing edge. Another important parameter when talking about the thickness is the maximum thickness location. And I've got some typical values of both the thickness to chord ratio and the location of the max thickness. Right there, those aren't hard and fast rules, that's just kind of like typical values for you. All right, camber. Actually, let me cover number 8, mean camber line, before I cover number 5, camber. So the mean camber line. Now, mean is actually because the camber line is it's the mean point, the midpoint between the upper surface and the lower surface. So it's almost like if you took all of the mid thickness points and turned them into a line, that would be your camber line, your mean camber line, or camber line. It's right there, number 8. You see it's got that dotted center line right there. That's your mean camber line. Once again, if you're dealing with the symmetric airfoil, that's just going to lie on top of the chord because there is not going to be any camber. But since this is a cambered airfoil or curved airfoil, there's going to be a mean camber line, just a line that's the mid thickness. Now, camber is the distance from the chord to the mean camber line. And one of the important parameters when we talk about camber is the max camber of the airfoil. The Yeah, and usually it's normalized to the chord, so it's kind of gets you a percentage value. The distance above the chord divided by the chord gives you percentage of the chord. These are usually less than 5%, but that's definitely an interesting value that we use. So that's something you're going to need to pay attention to. And it's actually, yeah, Camber's number 5. It looks like the image isn't very clear up between 5 and 9, but 5 is actually pointing to that line with the 2 arrows on the end. 9 is actually pointing to the lower surface of the airfoil. Now the upper surface and lower surface is just the surfaces that are the shape. It's just the line that you get if you take from the upper surface would be from the leading edge to the trailing edge. It's the upper line, the outer mold line, if you want to call it that, of the airfoil above the leading edge and trailing edge, and the lower surface would be the shape or surface of the airfoil below the leading edge and trailing edge. And we kind of already talked about trailing edge when we talked about leading edge. We talked about main camber line. Just another parameter that's on the illustration, as you see, there's just alpha, the angle of attack. That would be the distance from, or sorry, the angle between the chord line and the flow that's coming into the airfoil, the velocity coming into it. So it's just that distance between, or the angle between the chord and the flow velocity. So those are kind of some of the basic parameters, some of the basic geometry of the airfoil, and we'll talk later about some of the commands and capabilities that Xfoil has to adjust some of these values, which will give you different airfoil shapes, which will give you different performance of the airfoil. But we'll cover that in a future video. Alright, we're going to go ahead and end the video there. If you like what you saw and you're wanting to see some more from this channel, then go ahead and show some support, show us some love. Like the video, comment below, subscribe. All of these things help us know that you like what you see and you want to see some more. In the next video, we're going to have an overview of Xfoil, talk about some of the data flow, some of the general processing, some of the general paths that are taken when through the menus and through the commands when you're doing some basic analysis. So it'll definitely give a very good kind of top level big picture view of Xfoil. I think it's probably going to become one of the key videos in this series, and definitely a very good introduction into the capabilities and kind of the overall general structure of Xfoil. So I think it'll be really good. So once you like the video and comment below, go ahead and click the link on the next slide to watch the new video. I will see you in the next video.